So the case study we chose was the DC-10 Sioux City accident, and basically this was an airline accident that was caused by fatigue failure in a fan disc. So before the disaster, United Airlines Flight 232 took off from Stapleton International Airport in Denver, Colorado at 2:09 p.m. with 296 passengers and crew on board. And the airplane, you see it over here, was a McDonnell Douglas DC-10, and it had 3 General Electric turbofan engines. And the tail-mounted rear engine, which ended up being the engine that suffered the fatigue failure, it had accumulated 42,000 hours of operating time prior to the flight. So the failure, as you can see here, occurred in the fan disc, and it was discovered mid-flight during a turning maneuver when the pilots felt a jolt and the autopilot disengaged. And this jolt was a result of this catastrophic failure here, and the fan disc detached. And then engine debris shot throughout the tail, and this destroyed all 3 of the redundant hydraulic systems, and that resulted in a complete loss of control surfaces for the airplane. So unfortunately, the consequences of this failure was that the plane had to crash land in Sioux City, Iowa. But despite the complete loss of control surfaces, the pilots were able to maintain some control of the plane by using the separate throttles on the separate engines. But unfortunately, the high landing speed caused the plane to catch fire and break into pieces on the runway. And of the 296 people on board, only 184 survived.
The National Transportation Safety Board were the ones who investigated the accident, and they determined that the root cause of the failure was due to impurities in the titanium in the blade disc, and this had been due to something called alpha incursion in the manufacturing process, which is when oxygen is exposed to the metal in the forging process, creating small impurities which lead to stress concentrations which over time propagate into cracks and eventually resulted in this failure. And when the turbine was investigated, it turns out that the crack was visible and missed during inspection, which could have prevented this failure. The fix that was decided was to implement a 3rd vacuum process and increase the temperature during forging of the titanium components. And the reason for this was before there were only 2 vacuum processes, and it's evident that the 2 vacuum processes were not enough to completely mitigate the impurities, and also increasing the temperature decreases the chance of those impurities. Once this fix was implemented, no more failures were documented, so it's safe to say that the fix was sufficient in eliminating any impurities in the titanium. The design improvements, such as the 3rd vacuum for the titanium forging, were implemented at the time and were effective, but now that time has passed, it is possible to use newer, higher quality metals for the engine components, and also newer manufacturing techniques such as increased quality control and the use of automation to have robotic accuracy with no human intervention. Here are the sources we use to gather our information, one of them being Britannica Encyclopedia, and the other being an excerpt from the South City Journal.